We're very lucky to have Professor Alexander Fetter here to give us actually 2 talks today. He's going to give the colloquium now, and then at 5 o'clock in room 190, he's going to give the seminar that he intended to give yesterday but couldn't because of flights canceled out of San Francisco Airport. Professor Fetter was educated at Williams College, at Oxford, and then at Harvard, then went to Berkeley for a postdoc, and in 1965 drove down to Stanford, where he's been ever since. He's been one of the leaders in the theory of superfluidity and superconductivity and other aspects of condensed matter physics. Wrote an excellent book with Willechka on mechanics, and he's going to give us a nice talk on right.
Thank you very much. It's a pleasure to be here. And
do you prefer lights or
lights must be
or would you rather that we dim the lights?
I don't need them. Do you want to turn the lights on?
Well, we certainly have to turn this light on.
Yeah, at least that one, and we can't see the screen.
Just turn the lights off on the screen.
Yeah, that's what I'm trying to. All right, that's
Is that okay?
Now I can leave the others on, but
That's fine.
all right, okay.
So I want to tell you about a field that is, I guess, developed over the last more than 15 years, and it's really a lovely example of quantum physics. I gather that there's not a lot of condensed matter physics here, so I want to review the basic physics of Bose-Einstein condensation. The workhorse theory is something called the Gross-Pedievsky equation, which is an equation that turns out to be more powerful than it has any right to expect. I want to show you why, as you go to a rotating system, it becomes favorable to put a vortex in the system. And then I want to give some pictures of systems with vortices in them, the kind of thing that you cannot do with liquid helium. And I want to talk about 2 regimes of rapidly rotating condensates. The last one is basically mean field lowest Landau level regime, which makes connections with bosonic analogs of quantum Hall states. And then if you rotate even faster, there is, at least predicted, but has never been seen, the idea of quantum phase transition from a superfluid state to a highly correlated non-superfluid state, which has wave functions, many body wave functions that look like those for looks like those for various analogs of quantum Hall states, like a bosonic Laughlin state. So this is what I hope to cover. PEC appears in many contexts, especially superfluid helium and dilute Bose gases. The GP equation is an accurate description. Quantized vortices are crucial in understanding how superfluids rotate. The GP equation correctly predicts the actual dynamical motion of a vortex. You can study that experimentally. The rapidly rotating condensates have arrays of many vortices. Eventually, the vortex cores overlap, and at that point, you have to go to this lowest Landau level description. And eventually, you're going to go to highly correlated Laughlin-like states. So let me review the basic physics. Imagine you have a uniform gas of particles, n with number density n and mass m. The interparticle spacing is of order n to the minus the third, and that's one of the characteristic lengths of the problem. An atomic physics point of view takes one way of figuring out when it's going to go quantum degenerate. You define the mean thermal momentum through P thermal squared over 2m as the order kT. Then you use the de Broglie relation to get the de Broglie thermal wavelength, and you compare the thermal wavelength with the interparticle spacing. And in the classical limit, the de Broglie wavelength has h in it, and it goes like 1 over t, 1 over root t. So at high temperatures in the classical limit, lambda is very short compared to the interparticle spacing. And in that regime, the quantum diffraction effects are negligible. It's like ray optics for light. The dimensionless parameter n lambda cubed is called the phase space density. That's something they use in atomic physics all the time. And that's small in the classical limit. As the temperature falls, lambda grows, and eventually n lambda cubed gets to be 1. And it took 5-10 years experimentally to get to this regime. And you define Tc for Bose-Einstein condensation, where n lambda critical cubed is a calculable number of order 1. It's done in textbooks. Now the crucial idea is that for T less than this Tc, you start to get a macroscopic number of bosons in the lowest single particle state, if these are non-interacting bosons. You get N0 in it. And the fraction of particles decreases, and in an ideal gas at 0 temperature, all the particles occupy the same single particle state. So instead of thinking about a many-body wave function, all you need to know about is the single particle ground state that you study in junior or senior level quantum mechanics. And a dilute Bose gas has a very small density, these experimental systems. The number density is 10 to the 13 per cubic centimeter. Well, that sounds high until I tell you that the number density in this room is 10 to the 19 per cubic centimeter. So this is 6 orders of magnitude more dilute than the air in this room. And that gives you a very low transition temperature, the order of microkelvin. Now, this is the way I learned about it when I was studying this. You can think of a condensed matter view where you say each particle is in a box surrounded by all the other atoms. So you have a little box of order n to the minus 1/3 in size, and you all know how to calculate the 0-point confinement energy, say a spherical box. Now at high temperatures, kT is much bigger than this h bar squared n to the 2/3 over n. But as you lower the temperature, eventually these become comparable, and this is the usual estimate of when a dilute quantum gas becomes a dilute gas becomes a quantum gas. And you see it goes like n to the 2/3 over the mass. And for the Bose system, this is the same criterion as you got from the phase space density. But for a Fermi system, this gives the usual Fermi temperature. And if you do this for an electron, where the mass is the electron mass, you get the order of 10 to the 4 Kelvin, as we know. For helium-3, for liquid helium-3, the number density is about the same, but the mass is bigger by 10 to the 4, and so you get the order of 1 Kelvin. And in a dilute Fermi gas, you get a number typically in a microkelvin, the same as we got for the Bose gas. Now, the new feature in all of these experiments in the 1990s was the idea of putting them in traps. And so you start with a spherical harmonic trap, 1/2 m omega squared r squared, an isotropic trap. And it's a simple exercise to show that the ground state wave function for that is a Gaussian. E to the minus r squared over 2d squared. And the d is the oscillator length, and familiar quantum mechanics gives you the square root of h bar over m omega. And so this is not something you study in typical textbooks, but it will be. It's not hard. And if you put n particles in a spherical trap, KTC is of order h bar omega, which is the only energy in the problem, times n to the 1/3. And typically you have 1 million atoms, and we put in numbers, you again come up with this, the order of 1 microkelvin. Now, the interesting thing is, near TC, there's a big thermal cloud. And the thermal cloud is just a Boltzmann distribution with this potential. And so you get e to the minus b, which is another Gaussian, because the potential is r squared. And this gives you a thermal radius, which goes like, well, it's written down here. And so you get two different Gaussians. Above TC, you get this big fat thermal cloud. Just below TC, the narrow condensate starts to appear, which is this is D and this is the thermal cloud. And at 0 temperature, you see there's no thermal cloud. All you see is the condensate. This picture was on the cover of Science magazine in 1995, and I think it's very persuasive evidence that this is really BEC. And experimentally, you find the ratio of these two lengths is of order 10. Now, when you think about it, you're putting all the particles at 0 temperature into this Gaussian ground state. And that means that the condensate density is definitely non-uniform. It's a Gaussian. It's capital N times the density of the psi squared. Here it is. And so one of the interesting, challenging features is you're not dealing with particles in a box with uniform states, but you're dealing with these non-uniform states. And so the density varies significantly across the condensate. Now we need to put in interaction potentials. There's a famous paper by Bose-Einstein in 1947 who made the simple observation that if it's a weak interaction potential and T is much less than Tc, most of the particles are going to remain in the single particle condensate. And Bose-Einstein developed a canonical transformation. You write down a Hamiltonian, it's really elegant, and you write down the ideal gas Hamiltonian and then a correction that comes from the interactions. But because the interactions are weak, you can use a canonical transformation to solve the problem. And the beauty of that is it's non-perturbative. So all the effects that come out, all the interesting effects in many-body physics, the BCS superconductivity, the BEC transition that Bose-Einstein described, and the charged electron gas all have non-analytic behaviors. And you can't solve them easily with perturbation theory. And so this is an example, I'm not going to go into it here. The interesting feature is that the interparticle spacing in these gases is of order of a few hundred nanometers. The interactions are short range, so you can treat them with a scattering length, S-wave scattering length, and the S-wave scattering length is of order a few nanometers. So there's a factor of 100 here between this and this. And so you can approximate the interaction potential by a pseudo-potential or a contact interaction with a three-dimensional delta function, G. And G is made up of this characteristic quantity involving the scattering length. And in a dilute gas, we require that the density times A cubed is much less than 1, which is well satisfied. It's more like 10 to the minus 6. And the interesting thing is, and this is the heart of the matter, each particle in the condensate, in addition to having the kinetic energy and the energy in the trap, feels a mean field energy from this contact interaction with all the other particles locally. And so you just add a term to the Schrodinger equation, it's a Hartree term, and it's just G times the local density, which is G times psi squared. And the interesting thing here is that this is manifestly quadratic in the wave function. And so that appears in what's called the Gross-Pedievsky equation. I mean, once somebody's done it, it's so simple and obvious, but nobody did it before. This is the kinetic energy, the trap energy. This is the mean field energy. And this is called the nonlinear Schrödinger equation, or the Gross-Pedievsky equation. And mu is the chemical potential. You have to solve this equation self-consistently. Now, if you have a uniform gas, there are only two lengths, the scattering length and the interparticle spacing. But as soon as you put it in a trap, you have a third length, the characteristic scale of the trap, say d. And when you look at this in a variational sense, you see you've introduced a new dimensionless parameter, and you have to go through it. But the new dimensionless parameter is the total number of particles, the scattering length, divided by d. Now, a over d is small, 10 to the minus 3, but if n is 10 to the 6, na over d is big. It's like 1,000. And so the effect of this, even though it's dilute and weakly interacting, the effect of the mean field energy predominates over some of the other terms, typically. And depending on the regimes, you throw away one or the other of these other terms. Because Na over d is large, that expands the condensate, typically by a factor of the order of 10. And so the radial derivative is very small, just because the radial derivative scales like 1 over r, and r is increased by a factor of 10. You get 1 over r squared. So the kinetic energy is smaller by a factor of 100. And you just cross this term out. When you've done that, you see you get just an algebraic equation for the density. And this is called the Thomas Fermi limit. So you get an explicit expression for the density involving the chemical potential minus the trap potential. And by using this you determine, integrating psi squared, you determine mu as a function of the total number of atoms that you put in. It's a very elegant problem. And so what you end up with this harmonic oscillator trap is an inverted parabola. So the density distribution is just a 1 over r squared. I mean, 1 minus r squared over capital R squared. And capital R squared is just the classical turning point in that trap potential. And this is used all the time. So, in 1961, Gross and Pedievsky, independently, one in Russia and one in the US, wrote down a time-dependent version of these equations and looked at specific solutions. And it gives you detailed properties of the ground state. If you make it attractive, it gives you time behavior of the collapse, and it gives you frequency of the low-lying collective modes, and they are accurate at the 1% level, which is actually pretty amazing. It comes in two different forms. You can write it as a nonlinear Schrödinger equation, and this is probably the most natural thing you might first try. You see, this is the same thing we already had, and all you've replaced the mu psi by IH d psi dt. And you can think of this as arising from a Gross-Pedievsky energy functional, which is the kinetic energy, the trap energy, and the interaction energy. These are both quadratic, and this is ordered. And if you want to look for equilibrium states, you want to minimize this energy functional subject to fixed normalization, namely the integral of psi squared equals n, and that's where the chemical potential comes in as a Lagrange multiplier, which you're familiar with in grand canonical ensemble. Now, an alternative approach is to take hydrodynamics. You write this as a phase and a modulus, the density is psi squared, the velocity is h bar grad s over m, and that's very important in the quantum aspects of it. And you've got a particle current, which is the number density times the velocity. Now, in classical hydrodynamics, you define something called a circulation, which is the line integral of the velocity around a closed path, c. Here, the velocity is proportional to the gradient of the phase, and the line integral of a gradient is just the net change around the closed path. And so, the net change of the phase around a path in a quantum wave function has to be an integer times 2 pi. And so you get quantized circulation. This is well verified for superfluid helium, although it's a little indirect. I mean, everybody believes it. In 1949, famously at a conference, Onsager remarked in a footnote, or in a question, which appeared as a footnote in the written version, circulation of the superfluid is quantized in units of h over m, period. That's all he said. Nobody understood what it meant. I mean, if Onsager said it, it was presumably true. And then in 1955, Feynman wrote 3 or 4 beautiful papers on phonons and protons in helium in 1954, great papers. And then he wrote a review article in 1955 in which he gave this argument that because wave functions have to be single value, you get this quantized circulation. And then, of course, after the argument's so simple. Again, you wonder why nobody figured it out before, but people weren't so, superfluid helium wasn't much of a hot topic. The hot topics were nuclear physics and high energy physics. And so, I mean, the fact that Feynman was interested in this was considered kind of strange. And in 1956 and 57, Li, Yang, and Huang wrote a whole bunch of beautiful papers on the dilute Bose gas. This was after they'd done their work on parity violation and weak interactions and won their own Nobel Prizes. In type 2 superconductors, you get the same quantized circulation, except it becomes quantized flux. Now, if you take this representation, for historical reasons, this is often called the modeling representation, because I guess modeling in the 1920s used this representation to write out the Schrödinger equation. And the imaginary part gives you conservation of particles. So it's nice that all the hydrodynamics falls right out, and you get a generalized Bernoulli equation. And all the physics of compressional irrotational hydrodynamics is built into this GP equation. So let me tell you about a single vortex. Gross and Pedievsky studied the structure of a vortex, and this was their original motivation. Classically, a vortex can have any size in a hydrodynamics. But what they showed is the size of a vortex in this model is determined by quantum mechanics. H bar plays an essential role in the interaction. So you assume a very simple wave function, e to the I phi times a radial function in 2 dimensions. And if you take the gradient of this phase, you get a velocity that goes like h bar over mr times a vector in the circulating direction. It's just like a tornado or a hurricane. But it diverges as r goes to 0. And if you take the curl of this velocity, you get a delta function at the origin. It's analogous to what is the divergence of a point charge in 3 space. It's just a 3-dimensional delta function at the origin. And it's 0 elsewhere. It's just the same way the vorticity is concentrated on a line. Now, I'm not going to go through all of this, but there's some interesting features. The chemical potential is G times N, or A times N with some constants. The the speed of sound goes like the square root of mu. So if you want a real speed of sound, you have to have a repulsive interaction with A positive. And that's important. If you write down the radial Schrödinger equation, you see you get a centrifugal barrier that forces the wave function to go to zero at the origin. And the characteristic scale of that is determined by balancing the kinetic energy with the interaction energy. And since the kinetic energy has h bar in it, this is the characteristic length you get. Psi is the core size. You get an h bar, and you get this in the denominator. And it turns out that the circulating velocity becomes supersonic when the distance from the core is from the center is of order psi. So you can think of the vortex core as forming because of cavitation. It goes supersonic. You can't support negative pressure. Now let me tell you about a single vortex in a single large condensate. You can take, because one of the beauty of these traps is they don't have to be spherical. You can make them totally asymmetric, but it's simpler usually to make them axisymmetric. So you can put in a radial frequency and an axial frequency. If this ratio is very large, it means that it's highly squeezed and becomes a disk. If this ratio is very small, it's tightly confined radially, and you get a cigar shape. And now the interesting thing is what happens when you rotate. And it's not a hard exercise to show that the Hamiltonian in the rotating frame becomes h minus omega Lz. And so the functional in the rotating frame is the original GP functional minus this extra term, which is just this term. And so it's this energy E prime that I'm going to look at to study the behavior of a vortex. I'm going to skip this. So I'm going to use this E prime minus E equals E minus omega Lz to find the energy in the rotating coordinate. And first I'm going to evaluate it for a vortex-free condensate. And that's just because Lz is 0, it's only this term. And then I'm going to put a vortex, a straight vortex, a distance r0 from the symmetry axis with a rotation speed omega. And I'm going to assume it's a flat disk because I want to study a straight vortex, which is a good approximation, except at the outer edges. And this will include all the circulating energy, and the density is unaltered except for the small core. Now I'm going to say the extra energy associated with the vortex is just the difference of this energy for one vortex off axis minus this energy for no vortex. And this energy, as I'm going to explain, you can think of as characterizing the global and local stability of a vortex in a system as rotating with angular velocity omega. So I'm going to plot delta E prime as a function of displacement r0 for fixed omega. And let's look at curve A, which is for omega equals 0. So this is just, if you put a vortex off axis at various distances in a flat pancake condensate, you notice that the energy decreases monotonically from 1 normalized to 0 when it gets to the outer boundary. If there's no dissipation, the energy is fixed. If the energy is fixed, you have a fixed value here, and that means the position of the vortex is fixed, the radial position. So the only thing the vortex can do is precess uniformly in a circle at fixed distance from the origin, from the center. And you can show, and I'm not going to show you, the precession rate phi dot is proportional to the negative of this slope. And so if you do this, in this case, a positive circulating vortex will precess in the positive direction. Now you can easily, the reason this picture is pretty is that if you put in weak dissipation, you can understand that the vortex is going to slowly move down this curve and eventually disappear at the outer edge. And that physically means that it's going to slowly spiral outward with many, many rotations, assuming it's very weak dissipation. Okay? And now let's ask what happens when you rotate. Curve B is the case for rotating with a characteristic, what I call metastable omega. It has this value, but it doesn't matter. What you notice is, at this point there is curvature at the center. At this point the curvature is 0, and at this point the curvature is changed sign. So if you rotate just faster than this angular velocity, you're going to get a local minimum in this curve at the center, and then it will have a maximum and go back down. Now if you put a vortex inside where the curvature is like this, then if you put on weak dissipation, it will move like this, it will move back to the center. And so that's the onset of metastability, because the vortex no longer disappears from the condensate, but actually moves back to the center of the condensate just because of the dynamics that you can understand from this figure. And so that's why when you rotate sufficiently fast, it's energetically favorable to put vortices in the system. And that's where you get this whole picture of using the energy minus omega times LZ to understand where the vortex comes from. Kind of stay here. Okay, so now I want to show you some pretty pictures. It's extremely difficult to take photographs of vortices in liquid helium. Richard Packard did it, but it took him 10 years of very hard work using charged electrons. And I won't even bore you with the details, but I'll show you the final pictures. The first vortices were made by Eric Cornell and Carl Wyman in 1999. They started from a nearly spherical rubidium condensate, and they used two different hyperfine components. So this was a little intricate. And this starts to talk about stuff that maybe you've never heard of: Rabi coupled condensates and Rabi coupling and Rabi oscillations. It's standard for quantum optics, but I never studied it, so I've had to learn all this stuff. They use coherent off-resonant electromagnetic fields to couple the two condensates. And Rabi oscillations are analogous to what you get in NMR. And I hope you've studied some NMR, because I'm not going to go into it. The NMR-like techniques, you can interchange one component with the other, just the same way. You can think of the two components as spin up and spin down, and NMR can rotate a spin up into a spin down. And so you do the same kinds of things. The beautiful thing about this is these two hyperfine states have slightly different optical resonances. And so by using two different lasers, you can take pictures of one component or the other component separately. And so you can do this imaging separately. You just add an additional stirring laser beam. At just the right moment, you turn off the coupling. And it took a lot of experiment to get this right. And you can end up with a vortex in one component surrounding a non-rotating core in the other component. And they took pictures. And now this is the beautiful part. These Rabi methods meant that you could measure the relative phase of the non-rotating core and the rotating vortex. And this is supposedly the cosine of the relative phase. And it sure looks like a vortex, because you see it looks like the cosine increasing from where the phase angle increases from 0 to 2 pi. I mean, it's not a great picture, but at least it's persuasive. This was the first try. This is what they published in PRL. This is before everybody was fixated on nature and science. People were very happy to get their papers in PRL. Now, this is the amazing picture of the precession. And this is the beauty because they could take pictures of one component or the other component. So you can see the light is the vortex and the dark is the core. And you can see that it precesses. This is the raw data. This is smooth with a Thomas Fermi picture. And you can see this is the precession. And in the course of 300 milliseconds, it executes one complete circle.
Can you explain what the track is? How is the rubidium?
It's a magnetic track. You use magnetic fields. You can create something that looks like x squared plus y squared plus z squared. You expand out with a constant. And you can add a constant field which shifts to zero. And because the spin adiabatically follows the local magnetic field, there are 3 hyperfine states, and only one of them is trapped. One is weak field seeking, one is strong field seeking, which is expelled, and the other is m equals 0 leaves the trap because it's not trapped.
Okay.
I mean, I could write it out for you. It's just Zeeman energy.
So it's a vertical magnetic field?
No, it's spatially varying.
It's a quadrupole.
It's a quadrupole trap. It's complicated. I've never worked it out. I just accept it on faith. I mean, it's simpler than what's called a Yalpi-Pritchard trap, which I can't even explain how that works. Multiple Helmholtz coils in multiple directions. But I don't know. You could explain to us how it works. I mean, it's just take it as given that you have these magnetic boxes.
Okay.
That's what I do. If I tried to understand every experimental detail, I wouldn't do anything. So you can see these are really beautiful pictures. It blew me away. There's no way in helium you could take these pictures because the helium core is the order of 5 or 10 angstrom. And there's no way you can see that with visible light. Whereas here, the core size is of order, well, normally in a single component vortex, the core size is of order, say, half a micron. You can't visualize half a micron with visible light. So I'll show you some pictures that Dalibard took in a minute. And the only way they can do that is to turn off the trap and let the condensate expand. And the core expands as a hole in the condensate. And then they take a picture, and the condensate, what you see is the expanded hole. But you can't do time-lapse pictures that way. Here, because you have 2 components with roughly equal numbers in component 1 and 2, you get a big core, which is of order 10 microns. And that you can visualize, as you can see in this picture. That's the trick that makes it work. This is the Dalibard. This was 2000. Almost immediately, Dalibard is an incredible experimentalist as well as being an incredible theorist. He's a sort of polymath. He took a long cigar-shaped condensate like this, and he had a laser which he toggled back and forth. He had used a mirror to make it jump this way back and forth. And then he slowly rotated the plane in which it was toggling. And he called it a laser spoon. And so as he rotated this laser spoon, it stirred up this condensate and created angular momentum in the condensate. And then he turned off the trap, and it expanded. And these are the pictures. 0, 1, 2, 3, 4 vortices. These are shot to shot. They're not the same system, and there's no dynamical information here. But for comparison, these are Richard Packard's experiments. 1, 2, 3, 4 vortices in liquid helium. This took Richard Packard roughly 10 years to take pictures of, whereas this was done in probably 6 months, maybe a year. And this is one of the techniques that everybody uses now in cold gases. Wolfgang Ketterle, Ketterle being Ketterle, did a much bigger system. And you can see, here's 130 vortices. And people were blown away from this because it's a clear triangular lattice, which is what people had seen in type 2 superconductors in the late 60s, early 70s. So, I mean, this shows the clear analogy between the superconductor and the superfluid. So let me tell you a little bit about the mean field Thomas Fermi regime. The first thing that's important is Feynman's argument for what's the vortex density in a rotating superfluid. In a rotating solid body, if you're rotating hydrodynamic viscous fluid, the velocity is omega cross r, as we all know. And this has constant vorticity. The curl of this is 2 omega. Now, each quantized vortex has a localized vorticity, 2 pi h bar over m. And in a rotating condensate, this is Feynman said, this mean vorticity, 2 omega, must be equal to the areal vortex density times the localized vorticity per vortex. And you get this result for the vortex density, which is proportional to 2 omega. Now the area per vortex is 1 over this. You can write that as pi L squared, which gives you a characteristic radius, which is the inner vortex separation approximately. And it goes like 1 over the square root of omega. Let me skip this. So you can be a little quantitative. If you take the kinetic energy of the condensate, you get the gradient of the phase and the gradient of the density. In the Thomas Fermi approximation, you neglect this because you say the density is slowly varying. And so what you get is just this quantity. This is now the full mean field energy. Now V is the velocity from all the vortices, but we're going to approximate the velocity from all the vortices by just the solid body rotation. And then if you put that back in here, you end up with a very simple energy, psi squared, and psi to the fourth. The only difference now is you have omega appears in it, because of that comes from the solid body rotation. And this looks like the Thomas Fermi energy for a non-rotating condensate, but with this extra, replace this part, omega perk, by this. Now that leads to a, I won't go through the details, but you get the aspect ratio changes because of omega appears in it. And you see, as you rotate faster and faster, the condensate becomes flatter and flatter, which is what you would expect because of centrifugal forces. And it's a diagnostic that you can use by looking at the condensate to figure out how fast it's rotating. And so this is Eric Cornell's picture of a non-rotating condensate. Now they rotate it. I mean, these are not always the same condensate, but they're roughly the same. If you're rotating at 0.95, you get something that's sort of quite flattened, and at 0.993, it's very flattened. And so I like these pictures because it makes it very clear what's going on. they couldn't rotate any faster because this became so expanded that the optical density was too thin to take pictures of. The local density was too small to photograph. Now, what happens when you rotate very fast? Eventually, the cores start to overlap, and then you get local variations, which are the same as the scale of. You can't ignore the density variations, and so you have to go back to your original Hamiltonian, and you write down the general two-dimensional energy functional because it's very flat, and you get a very familiar one-body oscillator Hamiltonian plus this interaction. The one-body oscillator has the kinetic energy, the rotation energy minus omega LZ. And it turns out this is one of the classic problems that you can solve exactly using harmonic oscillator ladder functions. Right and left oscillators. And you get two quantum numbers, n and n. N comes in with omega per plus capital omega, and this is omega per minus capital omega. And in this limit, this drops out. So the eigenvalues are essentially independent of n. So you get a massive degeneracy. And that's the same as what's Landau levels in a magnetic field. And so n becomes the Landau level index. And the lowest Landau level, n equals 0, is separated from the higher states with a gap, a big gap. And the point is that because this term, psi squared, is so small, somebody's phone, you can neglect this term and just deal with this. So you deal with just Landau levels. So the Landau levels are very simple. The ground state is just a 2D Gaussian, and the higher Landau levels have an m, which is non-negative, r to the m, e to the I m phi, which you can write as a complex variable, x plus I, y to the m. And so you just have this complex variable to the m times this ground state Gaussian. Now let's make a model where we take a linear combination. This f of zeta is just a linear combination of zeta to the m, with m being a non-negative integers. And that's just the definition of an analytic function. In fact, it's a polynomial. And a polynomial can be factorized. So you can write it as a product of factors that go to 0 apart from an overall constant. And if you look at it and think about it, if you go around any one of these zeros, you pick up a phase of 2 pi. So this wave function has a whole bunch of vortices, one with each zero. And once you know the position of the vortices, you know everything about the wave function, because you're working in this lowest Landau level regime. The most important feature here is that the many-body Gross-Pedievsky wave function is just a product of these one-body wave functions, one for each r. This is a coherent superfluid state. You get macroscopic occupation. It's just the Hartree representation of the solution. Now what happens if you want to go beyond where this breaks down? You define, suppose you have n atoms and nv vortices. You take the ratio, nu, which is capital N over the number of vortices. This is called the filling fraction, or filling factor, in direct analogy with quantum Hall physics. Experimentally, you have about 10 to the 5 atoms and about several hundred vortices. So experimentally, nu is the order of a few hundred. Numerical studies for small n, number of vortices, and variable capital N, show that the ground state is a coherent superfluid state for nu bigger than 6. But for nu less than 6, typically you get highly correlated states which are not superfluid. And the lowest extreme of that is the Laughlin state, which you may or may not have seen, but because you put a factor 2 here, this is bosonic, because if you interchange 2, Z1 and Z2, you get plus with a factor 2. Laughlin state had 3. But otherwise, this is just like the ground state wave function that Bob Laughlin wrote down. This is a highly correlated state. It's totally different from these Gross-Pedievsky or superfluid states. How do you get to this regime? Well, first of all, you need to make nu much, much smaller. You need the number of atoms per vortex to be the order of 5. How do you do that? Well, in principle, if you have an array of small condensates in an optical lattice, you might be able to do this. You need to rotate to a relatively high angular momentum state, and that has not been done. Another idea is to use, and this, I can't explain it, but even if you don't rotate the system, you can make the system feel like it's rotating with something called a synthetic vector potential. And that's a whole other talk which I can't give today. But it's an amazing field. And these, I mean, when I saw these pictures, I was blown away. You have a parameter delta prime, which is effectively varying rotation speed, even though nothing rotates. And you see, as you increase delta prime, you start getting vortices. They're not an irregular lattice, but still it's pretty amazing. And nobody yet has been able to make this work to get to these highly correlated states. And so we never may do that, but it's still interesting. So this is my conclusions, and I will stop here and happy to answer questions.
You didn't talk about the possibility of turbulence in this hydrogen regime. So if you start spinning these things so fast or try to stir up, is that something that would get in the way of getting to this highly correlated regime?
Well, there's a whole separate field of studying turbulence.
Yeah.
But you think of that, it's not like classical turbulence.
Mm-hmm.
It's quantum turbulence, which means entangled, a spaghetti of vortices. And there's a man named Tsubota in Japan who's made this living for the last 10 or 15 years using the Gross-Pedievsky equation to model these. And he starts with a few rings and lets them go. And each one evolves in time using the time-dependent Gross-Pedievsky equation. And they start to interact. And you end up with a mass which eventually settles down statistically. I'm not sure how much has been done experimentally. Most of the experiments on quantum turbulence has been done in liquid helium, where it's inferred but not visualized. Original experiments by Lyman used large thermal currents. And there's something called second sound in helium. And it's sensitive to the presence of vortices. And so he could infer this tangle of vortices by the attenuation of second sound. And I don't remember, he did a whole series of experiments. And then people do grid towing and all sorts of other things to create turbulence, like what they do in classical fluids. I haven't studied it much, so I don't know much about it. But there's been a whole cottage industry. There's a lot of people in cold gases, theorists, you usually want to go to finite temperature and time-dependent phenomena. And it's hard to get quasi-exact solutions. So there's 6 or 8 different approaches. And everybody has their own ideas of their approach is the best, obviously. And I've urged them all to choose one problem where everybody can work on one problem using their approaches and compare and see who agrees and what's right. But they're highly resistant to that for obvious reasons. So it's a great question, and I don't know the answer.
So it's more of a comment than a question whether you, so light propagation in optical fibers follows the same nonlinear Schrodinger equation.
Except you've interchanged T and Z.
T and Z are interchanged. So how much of, so I've seen recently people have got interested in observing Bose-Einstein condensation inside an optical fiber and so on and so forth. How much of this do you think would carry over? Are you,
Is
do
this
you
the
know
word?
much? Yeah.
Jacopo Carasato?
What's that?
There's somebody named Carasato who's read my Phys articles on this. I know him, but I don't know much about. He talks about BEC of photons, but I don't remember whether he puts it in an optical fiber context. I don't know. I've never studied it. He's in Italy, Trento.
Question way back here.
Shout.
Yeah, I was going to ask, are there conditions under which the sizes of the vortices can get so large such that they merge?
No, you don't like to have doubly quantized vortices because the energy goes like n squared. If you have an n-fold vortex, e to the I n phi, because the energy goes like v squared, you get an n squared. And so a single n squared vortex, a doubly quantized vortex has nominally 4 times the energy. And so it likes to break up into 2 singly quantized vortices, plus kinetic energy. There's a beautiful experiment that was done in Ketterle's lab. And it would take me too long to explain how it works. But they could create a doubly quantized vortex by doing a magnetic field reversal in a quadrupole field. And they did create they could tell it was a doubly quantized vortex because if they waited the order of, I don't remember, 200 milliseconds, 300 milliseconds, it actually broke up into 2, they could see it break up and become unstable. So, I mean, there's evidence. In superconductors, you can control the, what's called the surface energy. And when the surface energy is, let's see, negative, you like to have a lot of vortices. Whereas if the surface energy is positive, you tend to have a few large quantized vortices to reduce the surface energy. And in a superconductor, by varying the thickness, you can increase the boundary scattering. If you make it very thin, there's a lot of boundary scattering, and that has the effect of decreasing the mean free path, and that leads to going from a type 1 to a type 2 superconductor. In a type 1 superconductor, you get these big flux bundles. In a type 2 superconductor, you get singly quantized vortices. And that's been observed. If you look at the way, if you take a disk of various thicknesses and study how the flux enters when you turn on a sudden magnetic field, in a type 1 superconductor, it enters in big bundles. Whereas in a type 2 superconductor, it enters and forms more like a lattice. So there's evidence in both superconductivity and these BEC experiments that you prefer to get singly quantized vortices, at least in the regime where you expect them. I can talk to you a little bit about it if you're interested.
Why don't we end now in order to give Professor Fetter a rest before his 5 o'clock talk in room 190.